So about this thing, Wayne. It's about the Hitchhiker's Guide to the Galaxy. I thought, oh, I don't need to watch that. The title says everything.
Oh yeah. Hitchhikers.
Right. Guide. So which way are we going?
Well, up, I guess.
Oh. I don't think hitchhikers flew. If they flew, they wouldn't need a lift, would they?
So maybe it's the fingers.
So follow the fingers.
Okay.
Alright. I mean, if they do that, they don't get anywhere, do they?
Not really, and they get a bit dizzy.
Yeah, they get really dizzy. That's why they need lifts.
Ah.
Solved it. So, I don't think you see the film. I think there's not much point.
No, not much point. It's
Got a
not
towel
worked
anyway.
out.
Yeah.
So we're on to a new type of field now.
Yeah, we've done football fields.
Done rugby fields.
Now we're going to do magnetic fields.
Quite different.
Yeah. If you happen to notice other fields, a field is a place where stuff acts.
Yep. So in this case, it's going to be where the magnetic field acts.
Yeah, so stuff being magnetised. So we have a wire, and the wire has a current in it going this way.
And this is just a straight long wire coming up. So it's suspended.
So this is when we become hitchhikers.
It is. Because what we can do is because the current flows through a wire, that induces a magnetic field, and we can work out what that would look like.
Yeah, and we use this rule. So our
That's the
thumb
right hand.
is the direction that the current is going. It has to be a right hand as well, yeah.
So it's pointing upwards, the current is upwards, it will tell you that in the question.
So it's going around this way.
You're following your fingers.
Yeah. So when to draw that, I'm going to draw looking down, so you're seeing it from bird's eye view. So this is it coming out towards you, so it's going anti-clockwise.
Remembering arrows are important for the direction that it's going round. Because if you were to use your left hand rule, it would be going around the other way, and that's not right. That is actually important that you use your right hand.
Yeah.
And yeah, this is if the current is coming towards you, so the thumb's pointing towards you, you'll notice the fingers are pointing in the direction of Trip's arrows here.
Yeah. And this is quite simple, so they don't often ask questions about that.
They don't. What they more like to do is take the wire, coil it up, and give you a horrible time.
Yeah. So that's what we're going to do as well. So we have some coiled wire. We often call it a solenoid. So stuff goes around. In the exam, they often draw it in a way that we're not very good at drawing it, so that's why we've done that.
Yeah.
But they do that, and then this is it going down. And
yes, because it's going into the board. You've got to imagine this is like a spring going into the board like that.
Yeah, but we're not very artistic, so
we're going to stick with this model.
Yeah.
And the current goes in one side.
Okay, and out.
And out the other.
So the thing about this rule and coils is quite tricky to follow. So you
take your right hand rule, you go upside down,
and then
you break your arm.
So that's bad. And if you're left-handed, you can still write, but you haven't got a right arm now. So
what can we do to visualise this easier?
Well, we can make a model.
We can indeed.
And then form now.
So this is just these are the little hill things you get for cars when you're a child. You put a car on it and it goes round and round and round. But it looks a bit like a solenoid.
Yeah. So as you can see here, it's going round and stuff.
Yep.
What we're going to do is we're going to cut it.
So we take a copper cutting knife here, and cut along. So now I've only got half of the coil left.
So now you
can now visualise it.
Yeah, in 2D rather than a funky thing.
So if you're looking at this face on, after we've cut it, there's a point here. And
there is. Here. The point here is where the wire goes in, so this will be with a circle with an X in it, and you go around, and then the point comes out, so it'll be a circle with a dot in it. Now this is when we can think about the direction our current is going in each of these cases. When it's going in, like Wayne is drawing now, it's like this.
It is indeed, so that's what it would look like on all of these top bits all the way along. So you get your thumb, you point it in, and which way is your fingers pointing?
So you follow it round, and this one is going anti-clockwise.
Yep.
Yeah.
And let me just double check.
Yeah.
It's going that way, it's going that way. And that would be the same
clockwise, sorry.
For all of these. So the arrows on the inside are pointing this way, and the arrows on the outside are pointing opposite to that.
And you do it the same with the bottom one, so the thumb is pointing out here, and this is the one that goes anti-clockwise.
Follow your hand round,
so then
going this way.
And what they often do is they ask you which direction is it going in the centre. I mean, they could ask for the outside, but
unlikely.
Yeah.
So all of the arrows on the inside are pointing this direction.
So net field is going this way. So the thing to mention about magnetic fields, an electric field is the direction that the positive charge is moving.
Yeah. And for your gravitational field, if you put a thing with a mass, it goes towards the greater mass.
Yeah.
And that's how you think of the field lines.
In the magnetic field, it's the way the North Pole would move. So you're familiar with your North and South Poles.
So, I mean, you couldn't just get a North Pole, but if we say for a second we could just get a North Pole and put it here, it would fly that way because it's being pushed that way.
But what we often do is use it in electromagnets.
It is. So we have an iron core. If I just have a lump of iron core, it's not a magnet.
No.
But if I put it inside this coil, so we've got a lovely big magnet that sticks out either end in this case.
Then we have something we can use this for. So as our wire, as we showed here, the magnetic field lines will go in this direction.
Yeah, we're going that way.
So this end must be our north pole.
Yeah, because all of the north will be pushed to this side, and all of that, so it actually becomes a magnet when there's a current. So how can we increase the strength of this magnet?
We add more coils.
Or a much greater current. Problem with a much greater current is that leads to a much greater temperature. So more commonly you do more coils around it, and that will make it stronger.
But they do use very large currents. The problem with big large currents is, as Wayne said, it gets very hot.
Very, very hot.
But they can get around that.
They can, and they use superconductors.
That is what they do. They get really cold and there's virtually no resistance. And that's when they use electromagnets quite a lot. They use it in MRI.
They do, and we get onto MRI a lot more later on in the course. In detail.
Yeah, we sort of work out how it actually works, but that's magnetic resonance imaging, they use it for that. Picking up big cars.
Yep, so scrapyards use them when they're hanging the cars on it.
If you do
chemistry, we can use these sorts of things for infrared spectroscopy and stuff like that.
Yeah, and mass spec and stuff, and
motors and stuff like that.
Yeah, and particle accelerators.
Yes.
So they're really useful things and very much more powerful than normal magnets.
So that's electromagnets.
Yeah.
Let's go on with the course and see where it takes us.
Alright. Now I should probably watch that Hitchhiker's Guide to the Galaxy thing.